Yeah. So today I want to walk through some kind of problems related to that. If Yeah, so we'll maybe touch on a little bit of how we got here, but we're gonna work through some problems, assuming that we kind of are all at least somewhat on the same page as far as what we're trying to accomplish. So I'm gonna work through a set of kind of example problems. Of course, feel free to stop me, and I'd love to answer questions along the way, and get a sense as to where the tricky parts are for you all. But I am I'm uploading just it's a file, a Word file to Canvas, which you don't need to pull down. We'll talk through these all, but if you want to kind of look at what questions I'm gonna work through, it's now on the home page, under Chapter 7. I think it's listed Chapter 7 Friday lecture questions. And we may not do exactly what's on there, but that's kind of the rough outline that I want to talk through. And yeah, so we'll jump into that if I get these things out of the way. And we will turn on this. Okay, so yeah, so I want to focus in on one example, simply to kind of keep our numbers easy to keep track of. And so what we're going to focus in on is another normal distribution. And this one, again, shows up in biological situations, and that is blood pressure. And specifically, we'll focus in on systolic blood pressure. And don't ask me to, give you the a good medical understanding of the different blood pressures. But other than to know that we want it in a certain range. Okay, so when you go get your blood pressure checked, a lot of you are young enough where hopefully you haven't had it checked too much. It's usually when something's going wrong or when you get old. But yeah. And yeah, so we're gonna talk about the systolic blood pressure, and that is a distribution that has it has a mean of around 112, and we'll just call it that. We'll round it to that. I don't know exactly what it is, and it has a standard deviation of about 10, or those are the numbers we're going to use. So that means not everybody that goes in and gets their blood pressure checked is exactly at 112. There's some type of a range of outcomes. And now this is, importantly, this is for healthy adults. Okay, and so we can use that information to potentially, the fact that it's for healthy adults means that we can use that to flag and maybe find unhealthy adults. And that's often why your blood pressure is checked. We check to make sure that it's within kind of a healthy range. Okay. And so we're going to walk through some examples. Again, I have some of the questions listed on that file that I uploaded under the Chapter 7. But we can, again, answer any specific questions that you have. So feel free to stop me or ask different questions as we go. So the first one, I want to simply think about what percentage of people. Again, this is in the healthy population. So if there was just a random healthy person that came in, what percentage would have a systolic blood pressure between 115 and 125? And so I want, while I pull this up, you can take a minute and just see if you can figure out how we would go about that. Go. And this is just not liking me. Okay, so I was going to try to pull up the question there, but maybe we'll do that later. So between 115 and 125, how do we think about finding the range or the percent likelihood that a person would fall in between 115 and 125, or what portion of our population falls in that range? Okay, so again, I think the best way to start is to always draw the picture, because we're going to use our z-table, we're going to use our z-calculations to help us out here, but some of this is going to rely upon us keeping things straight in our heads. Nope, that's not what I want. Okay. So sorry, I'm just getting this pulled up so we can look at it later. So we have a range of outcomes that we're interested in, and we know certain things about the population. Okay, so we know the mean is 112, the standard deviation is 10, and so we can take these two values and turn them into z-scores. Okay, so the process in this case is going to be finding a z-score and then looking on the z-table to find the percentage, right? Because what we're after at the end of the day, we want to know what the percentage is. Okay, and so we're going to take our mean, standard deviation, and the x's. We're going to plug it in and find a z-score. We're then going to take and look up on the z-table. Okay, that's going to be kind of our flow. If I start over here, our flow coming this way. Okay, now that is going to be a typical flow of some of these problems that we encounter, but it's not always going to be. So if you've gotten into the problem set, you'll notice towards the end, there's some tricky questions there about finding the standard deviation. So the way we go about that is going to be slightly different, and we'll do an example problem here in a little while. Okay, so all of these problems are going to rely upon the z equation. Z is x minus mu divided by sigma, right? So this formula, maybe we'll just plop it up here. So we're going to be coming back again and again to this formula. And as I said, in this case, we know mu and we know sigma. Okay, so we're always going to be trying to fill out this formula. So if we know mu and sigma, let's plug those in. So our formula becomes z is equal to x minus 112 divided by 10. Okay, and here we can write the number 112 better. And now we can find what is the z-score for these various cutoffs, right? So what we're interested in is the range between 115 and, let's pick a different color, 115 and 125. Okay, there's a certain percent of likelihood that falls in here. And we're interested in the area in between. So we need the z-score for both of these. So let's go ahead and calculate that. So the z-score for the red is going to be 115. Oops. 115 minus 112 divided by 10, which gives us 3 over 10, or 0.3. Similarly, let's do the green one. That green value, the z-score is, what did we say, 125 minus 112 over 10, which is 13 over 10, or 1.3. Okay, both positive. Both of these are above the mean. Again, this is relying upon the concept that the standard normal, right? The standard normal being, just to kind of refresh from what we've talked about earlier, the standard normal being that normal from 0 with a standard deviation of 1, right? We can transform all of these normal distributions into the standard normal. Think about the area under a standard normal, and it's going to be the same relationship as our original way up there. So turning things into the z-scores, we can then look on the z-table, right? The z-table having done all of our gross calculations for us. Z-table, they've integrated from, we can look up 0.3 to 0.13. We can look up both those values on the z-table and find out what the likelihood of being in between those are. And then that's going to be the same likelihood as if we were dealing directly with our original systolic blood pressure distribution. So our next step, now we have a z-table, or we have the z-scores, right? So returning back down here, we have the z-scores. So now we can look up percentages along the z-table. So I'm going to pull that up. And remember, so I've posted this to Canvas, so if it's fuzzy or too hard to see, you can always pull that up there. Otherwise, it's also in the back of your book. I know you have an ebook, so I don't know if back makes any sense, but it's in your ebook under Appendix B. Yeah, I can zoom in a little bit here. So again, the z-table gives us very specific information, and we're going to need to kind of interpret what we can grab from them. So let's start with the z-score of 1.3. So when we want to look up a z-score, we first we look along the first column here, and we look for 1.3. Okay, and then we have to look into the hundredths place. So if, for instance, our z-score had said 1.33, then we would kind of come over to that value of 0.03, 1.33. Our case, it's 1.30, so we stay in that first column, and we find 0.4032. Okay, so 0.4032. Okay, I can get out of the way. So what does that tell us? That's a 40% likelihood. So a 40% likelihood that the person's systolic blood pressure would fall between what? Between 1.3 standard deviations and the mean. So that's not quite our answer. So really what we've found there is the green area shaded, but not just our window. It's that whole green area, right? It's from the mean to whatever our z-score is. Let me go the right way. So it's this whole, I gotta figure out this mirror thing. Okay, so it's this whole range here. But we only want this range. So how do we tackle that? Well, let's look up the red z-score. For our red, for the value at 115, we found a z-score of 0.3. Let me expand this again. So 0.3, looking it up on the z-score. Again, we come down to 0.3, and yet again, we're in this first column, so we don't have to go over any farther. We see 0.1179. 0.1179. Let me just circle that to have it stand out. And that's the likelihood, or the percentage associated with being between a value of 0.3 and the mean. Okay, so in this range. Okay, so we have now found the red shaded. Neither of these are our answer, but we can use both of those. If we subtract off one from the other, we can find our actual value that we're interested in. Okay, so all that's left to do is to say 0.4032 minus 0.1179, and that's going to be 38? No, 28. Check my math real quick. 3, that's 6, 39. Something like 28. Okay, you can verify if my math is right or wrong, but if I've done that correctly, we now know that 28.63% fall between 15 and 125. Okay, so it is a multiple step process, but just to reassess what we've done here, we knew the mean, the standard deviation, and the x, or the x's, right? We had 2 x's that we were interested in. We knew the mean and the standard deviation. We were curious about the percentage. And so we were curious about the percentage. We knew we had these, and so we could find a z-score and look at the z-table. Okay, so it's a progression of a process here. And again, what was helpful is that we kept track of what we needed to find by drawing a picture, shading it in, making sure that we knew what we were specifically finding with the z-score. Okay, so let's walk through, I think, the second question I have posted on that sheet, if you do have it up. I'm interested now in same scenario. Let's stick with the blood pressure. Still with a mean of 112 and a sigma of 10. I'm interested in, I've got all kinds of things on the screen here. I'm interested in what percent is less than 90. And here it's not really going to matter if we say less than 90 or less than or equal to 90. Again, because that exact location is essentially 0. Our math is not going to actually care if we're talking about 90. Okay, so similar process, because we again are interested in a percentage, right? We don't know the percent, but we do know the x, the mu, and the sigma. Okay, so we know x, mu, sigma. We're interested in the percent, so we can find a z-score, right? So because we know these 3 things, we know 3 out of the 4 parts of this equation. So if you have an equation and you only have one unknown, you can solve for that. So all we're going to do is plug in those values. It'll spit out a z-score. Once we have the z-score, we now know that we can just look up on the z-table what that z-score is associated with a percentage. And again, once we do that, we just need to keep in mind what area of the curve we're actually looking for. So let's just draw that in real quick. We have some value here at 90. What are we actually interested in? We're interested in what percent, what percent is in this range down here, this below 90. Okay, that's what we're trying to find out. So let's plug it into the z table. Sorry, let's plug it into the z formula. So z is 90 minus 112 over 10. So we get a z-score here of negative 22 divided by 10, or negative 2.2. Okay, important here that we have a negative score. Okay, so z-scores, again, we're talking about a deviation. So this is, this is a deviation, much like we did in standard deviation. But remember, in standard deviation, we square it. Here, we don't do that. We want to keep track of that negative sign. If only to remember or remind ourselves down the road. Okay, so we now have a z-score of negative 2.2. Let's take it to the Z table. If I can enlarge this. Okay, Z table, 2.2. There is no negative 2.2. Okay, so for sake of space, largely, and because it's repetitive, if we did another Z table with negative values, it would just be the exact same percentages listed here. Okay, so 2.2, again, we have 2.20. That's going to happen when you have a standard deviation of 10. So we're kind of living in this first column here because we all these have a 0 in the hundredths place. But we go down to 2.2. Again, we're right here, so we find 0.4861. 0.4681. That's not 0.4861. So 48% fall between the mean and 2.2. Notice, however, that this is positive 2.2. We just looked up the positive value. And you can always remember what this value is giving you on the Z table is that they give you a little picture here to remind yourself. Okay, so this is always, so in this example one, it's from 0 to 1.96, and that's the shaded region up here. So anytime we find a Z score, we're really moving along this line, and so we have 2.2. We're just out beyond this 1.96. Let's close that up. So we know that 48% fall between 0, a mean of 0, or in our case, the mean of 112, and 2.2 standard deviations. So we just found 48%, 48.61 are over here. Now here's where we rely upon the trick of it being symmetrical. So this is 2.2 standard deviations above, and this is negative 2.2 standard deviations. Okay, so the distance here is the same. And so the share of the region is the same. And so this, if we were to flip this over here, and this is getting quite gross, that would be the same share. Okay, so we can use the fact that they're symmetrical. We can also use the idea that either half has 50%. So again, this is why it's helpful to draw those pictures. So we know that 50% is this kind of larger area, right? Everything to the side of the below the mean. We also know that 48%, 48.61% would fall in this region. I can't reach over there. So that means the remaining percentage is really what we're after. Okay, so that, what is that? 1.39. Right, so we can use the idea that 0.5 is half of it, and we subtract off the 0.4861, and that should give us 0.0139, and that's how we get the 1.39%. So we know that 1.39% of healthy adults have a systolic blood pressure below 90. Okay, so the process is the same. We didn't know the percentage. We knew X, mu, and sigma, so we could find a Z, look it up on the Z table, and then we have to interpret the Z table results given our picture. Okay. So I think I'm gonna we can quickly walk through question 3 as well. Again, feel free to throw something in the chat if you have questions or interrupt me. But hopefully this is, after you see it a few more times, it starts to sink in kind of the flow of what we're doing. So we'll do it one more time real quick with question 3, and then we'll shift gears a little bit and answer kind of that tougher question that you might see in the homework. So yeah, good question. So the 0.5 is coming from the concept that let me just draw a picture that's not as messy. So because the whole of the normal distribution, all of this is 100%. Right? Every outcome has to be incorporated here. So the whole range is 100%. So because it's symmetrical, the two halves are equal, right? If we cut this, right, and this is not going to really probably work, but if we cut this and flipped it over, they would match, right? If I cut it and just folded it over, they would match perfectly. So because of that, that means that each of them is 50%. So either half has 50% of the likelihood. So we can use that to know that if I want to talk about an extreme end, and I know, let's say I calculate something where this is 35%. Then I know that the other part has to be 15%. Right? It has to equal 50%. So that's a trick that we kind of rely upon, and that's true whether you're talking above the mean or below the mean. Either half is 50%. Okay, so let's talk about one more kind of example in the same kind of workflow. So what if we want to know? I'm just gonna keep with the yellow here. So what if we want to know what percent of people come in and their blood pressure is between 92 and 132. Okay, remembering our mean is 112 with a standard deviation of 10. Okay, so quickly let's walk through this. So we need to find the z-scores, right? So we want to know percentage. We know x, mu, and sigma, so we can find a z-table, or we can find the z-score, look it up on the z-table. Okay, and in this case, we're curious about the percentage in between these two values. So let's crunch the z-scores. So again, z, x minus mu. So let's start with 132 minus 112 divided by 10. It's going to be 20 to... It's going to be 20 divided by 10. So we get a z-score of positive 2. We can quickly do the other one. 92 minus 112 divided by 10 is negative 20 divided by 10, or negative 2. Okay, so we have z-scores of 2 and negative 2. Let's go to the z-table, right? We have a z-score. Let's look up what that z-table is telling us. Again, we have 2.00, so we are going to be in this first column. But we go down to 2.0, we go over to the 0, we find 4772. Yeah, okay, so technically this is, so 0.4772. Okay. Now, while we're here, we've just looked up the positive 2, but remember, we get the same value for the negative 1, right? It's just symmetrical. So if we have negative 2, it's going to be the same value as well. So it's 0.4772. Okay, it's the area of the curve that they're talking about is different, but we get the same value. Okay, so let's get rid of the z table. move me out of the way. So we know that 47% are, or 47.72% is in, so the first one we looked up, the yellow, is actually this region, right? That's the straightforward Z table percentage. We also, with the -2, it's this area. And so now we don't want to subtract anything, right? So both of these we're gonna actually just combine them, add them together. So when we add these together, just add them together, we find, or this is going to be 95.44, I think. Or, sorry, 0.9544 or 95.44%. Okay. So again, you got to kind of keep track of, are you needing to subtract off between two numbers or add them together? Here, because we span across the mean, we want to take both parts and add them together. So we just calculated the likelihood of being between or within 2 standard deviations of the mean. This should sound a little bit familiar from a few chapters ago. What did we learn about the empirical rule? We found percentages of being between 1 standard deviation below and above the mean, 2 standard deviations, and 3 standard deviations. And we said the rule of thumb, or the empirical rule, was 95% of observations fall between 2 standard deviations. And that's what we just found. And in fact, it's almost exactly that. It's a little bit higher, right? So that's a little bit of an offshoot. So it's kind of a rule of thumb. The actual value is 1.96. So so plus or minus 2 standard deviations, go with sigmas, gives you 95.44%. Okay, and we kind of use that as a rule of thumb. If you wanted to know exactly what 95% is, it's actually plus or minus 1.96. That would give you 95.0%. But this is kind of where that empirical rule comes from. If we did that for 1 standard deviation, we'd get what? It would spit out 68%. And if we did it for 3, it would be the 99.7. Yeah, so that empirical rule that you learned a few chapters ago, this is where that's coming from. If we crunch the normal distribution Z tables for plus or minus 2 standard deviations, we get about 95%. Okay. And actually, that 1.96, that is the exact value. If we go back to the Z table, that's the kind of default that they give you, or the example that they give you up here. And that's why that one is used. Okay, so we'll have more to talk about that in the future when we get into p-values and understanding significance. That 1.96 is going to come back into play. So I just wanted to mention it here so you've seen it. Okay, let's shift gears and talk about a different example, and this is probably of most interest to you because you're going to have to do it on the assignment. And that is to go about this type of a problem slightly differently, or answer a slightly different question. So let's leave systolic blood pressure behind. And let's think about now I gotta find the. Let's say we have a normal population with a mean of 25. Okay, so let's say we have a mean of 25, and we know it's a normal population. And we also know that 25% fall below 16. So we know that if 16, I don't know what this could be. What would have a mean of 25? Gallons of milk drank per year. That seem it's one every like 15 days. That could be. So gallons drank per year by adults in Minnesota. We know that has a mean of 25. We don't know, but let's say we do know that, and we know that 25% fall below 16 gallons per year. So what we're interested in here is what is the standard deviation of the population? Okay, so we don't know what the standard deviation is. So we can use our same system here to solve for the standard deviation. And so let's kind of think about the workflow here. We don't know standard deviation, but we do know the x that we're interested in. We know the mean, and we know the percentage. Okay? So in some sense, we can use that to find the z. Whoop, off behind. We can use this to find the z, right? The percent and the z are connected, and so if we know the percent, we can find the z. And so what that means is when we turn to our equation up here, we will still be able to know 3 of them and solve for the 4th, right? Anytime we have an equation with only one unknown, we can just solve for that variable and we'll know it. Okay, so let's plug in what we know into the z equation. So we know z is equal to 16 minus 25 divided by sigma. We're not going to know sigma. That's what we're looking for. So we got to find z. And what is z? Well, we want a z-score that is associated with 25%. I realize I've made this. Okay. So let me alter this slightly. Is that a good idea? I don't like the 25% because it's symmetrical. So we could talk about why. Let's change this. Sorry if you've already started to do the work. Let's say 20% are below 16. Okay. We made this scenario up anyway, so I think this will be better. So let's talk about 20%. So 20% are below a certain value. So let's pull up the z table. And we want to figure out what z-score would be associated with 20% being below a certain value. So here, we're going to have to work through the z-table the other direction, right? The answer that we're looking for is a z value, right? So typically, or in the past, we've looked up the z that we already knew, and we've found a percentage. So all these values in the middle are percentages. This time we know the percentage and we'd like the z-score. So we work the other way in the table. So we want to find 20% below or 20% on the outside. Okay, so the z-table, again, let's set the z. Let's get rid of the z-table for a moment. We want to find 20% out here. So what is our z? Our z, when we look up on the z-table, that gives us the likelihood to be close to the mean, right? So what it's going to give us is some range here, which we know, again, is going to be symmetrical with this range here. So what do we actually need? We need a 30%. Right? We need to look up 30% on the z-table, which is going to tell us 20% is outside of that value. Again, that's going to be the same as if we, right, we're going to work in the positive z values, but it's the same on the negative. So we just want to find what likelihood keeps you, or what z value keeps you within, or means 30% are within that value to the mean. Hopefully that isn't too confusing. I said it a kind of an awkward way. So we need to find 0.30 on the z table, because that's going to leave us 20% on the outside. This is why I didn't want it to be 25, because that's going to give you the same answer. Okay, so back to the z table. So we need to find 30% in here, right? Because again, maybe it'll make more sense up here. We want to find 30%. What z value gives you 30%? That means 20% is on the outside. And again, because it's symmetrical, that means we can use that to be on the low end. So we want 30%. We're not looking at 0.3, right? That's the z value. We want to find 0.3 in here, and we find it up in this region, okay? That might be really hard to see. Let's zoom in. Okay, so we don't find an exact value. So we could kind of pick a value in between there, or just go with one that's the closest for ease. So what did we just find? We found that 29.95% at a z value of 0.84. So a z value of 0.84 would give you a 30% window. Okay, so let's go back. So 0.84, let's go back to what we're working on here. So 0.84. We knew that this was we want 30%, or we want 20%. But we needed the z value associated with that. So 0.84 would give us that cutoff. So we can plug that in to our z formula. So now we have let's just keep it over here. So 0.84 is equal to 16 minus 25 divided by sigma. And now all that's left to do is solve for sigma. So I'm going to come down here and say, so we're going to do 0.84 times sigma is equal to 16 minus 25. So sigma is equal to negative 9 times, or divided by 0.84, sorry. So, yes, 20 and not 25. Okay, good question. So, Nicholas asked, we're going to work with 20 and not 25. So I had 25 all over the screen. So I wanted to keep 25. What I wanted to change, sorry, I should have thought about this before, is that I didn't want it to be 25%, because I wanted to highlight again that we want to look up the 30%. We need to look up 30% and not 20% here. To get this cutoff of 20%, we need to look up 0.3 in the z table. The problem with 25 is you would look up 25 to find 25, right? So if we are interested in a 25% cutoff, we would look up 25%, and that wouldn't drive home the concept that to look up for a 20% on the outside, we need to look up 30% on the inside. So that's the reason I changed from 25 to 20. It was really the change of the percentage. And that's why we still have 25 as the mean. So sorry for that confusion. So we're looking for 20% that are on the extreme value, or the outside of this distribution that is centered around 25. So, yeah, so we have 9 or negative 9 divided by 0.84. Let's plug that in somewhere. 9 divided by 0.84, and that's going to give us a standard deviation of 10.71, roughly. Okay, and so now we know what this scenario says about the standard deviation. So we knew an x, we knew 16, and we knew that 20% were below 16, and we knew what the population mean was, 25. And so that suggested to us that the standard deviation was 10.71. Okay, so the workflow was different. We wanted to know the sigma. We knew these. We had to still find the z through the percentage, right? So we worked the opposite direction with the percent to the z score. But then again, all it became was solving for one value in our z calculation. Okay, so let's walk through that again. I have another question on that same sheet, if you're on that, and we'll do that. So let's say, for instance, we'll stick with the same population. It shows 10% are above 36. So same population, or what we're assuming is the same population, 25. And here we've said there's a value at 36, and 10% fall in that region. So again, the question is, what does this imply about our standard deviation? And so same process, okay? So we don't know the sigma. Okay, so sigma is unknown, but we do know the other things, right? So we know x, we know mu, and we know the percent, which again we can find on the z table. We can turn into a z. Okay, so our x is 36, our mean is 25, and then we need to look this up, right? This is a 10%. So 10% falling in that extreme part of the distribution means what? It means 40% are within that value, right? So what we can find then is what we're really doing is saying, what is the z-score associated with this value of 36? We want to know what z-score that's equivalent to. So we go back to our z-table, and we're interested in 10%, but because we want the outside 10%, we need to find 40% in our situation here. Let's see where we fall. Okay, so we need to zoom out. That's our problem. It's probably getting very small. So let me see. Let's do that. So we need to look up 40%. And 40% is, see, we're pretty close right here. So I would consider that close enough for our purposes. Again, you could find the exact value. It would be somewhere between 1.28 and 1.29, right? But pretty close to 1.28. And so probably rounds to 1.28. So the z-score of 1.28 is associated with 40% being between 1.28 standard deviations and the mean. 1.28. Let me just write that down so I don't forget. Okay, so 1.28, the z-score of 1.28 gives us that. And so now we can just plug it into our equation. Okay, so 1.28 is equal to 36 minus 25 divided by sigma. Again, so let's all we need to do then is rearrange some things. Okay, so sigma times 1.28, where's my decimal? 1.28 is equal to 11. So sigma is 11 divided by 1.28. And that gives me a sigma of 8.59. I'm in the way. So what we found here is that the standard deviation for this population would be 8.59. Now, we kind of worked through two examples with what might be the same population. But what have we found? We found the first one had a standard deviation of 10.71, and the second one had a standard deviation of 8.59. So this might be enough evidence to say this might not be the same population, right? The fact that they're quite a bit different maybe suggests that this isn't the same population. So for instance, what did we say? This was milk drank by adults. Maybe these aren't the same groups. Maybe we sampled some people in the city, in the Twin Cities, and then some people from rural Minnesota, and there might be a different relationship to milk drinking, for some reason. So the fact that we don't get a quite similar, now if it showed up as 10.71 and 10.62, we'd probably say, okay, that's pretty close. But this is the process through which we could find a standard deviation. And then if it's different enough, we would probably want to, so either say it's a different population or say it might not be normal. Okay, so again, a normal distribution is only one of infinite different types of distributions that it could be. So maybe milk drinking isn't normally distributed. And so if we've crunched the numbers based on this mean and the percent that are below a certain value and above a certain value, we might actually say it's not quite normally distributed. Maybe it looks a little different or it's skewed, right? There might be some skew to this. Maybe the distribution has, a negative skew to it or something. And so our calculations aren't going to work exactly right here. We're not going to get the exact percentages that we've been dealing with if we don't have a normal distribution. So I ask you to kind of work through a similar situation in the assignment, so hopefully this gives you some insight into that. I'll stick around and ask questions. I want to touch on one last thing, and that's the last part of chapter 7 that we cover, and that's approximating the binomial. So remember in chapter 6, we spent a lot of time talking about the binomial, and because it's used quite often. In fact, I was just watching, if you've never seen Moneyball, the movie Moneyball with Brad Pitt and Jonah Hill, follows the Oakland A's, and it's really about the influx of statistics into sports, namely baseball, but sports in general. And there's a brief moment, I think Brad Pitt is on a plane, and he's reading up on this stuff that Jonah Hill's character tells him about, and there flashes across the screen what hopefully is familiar to you now, that being the binomial calculation. So they're talking about wins over a certain amount of days or games left in the season, and you can see we have our 53 factorial over 41 plus 12 factorial, or 41 factorial times 12 factorial, right? So that's 53. So there's an N and an R here. And so they're talking about the likelihood of winning, say, 41 games out of 53. And again, you can see the pie. They've associated 52% as your chance to win one of the games. And so I just thought it was interesting if you've seen the movie. If you haven't seen the movie, or if you want to rewatch it now that you have a little broader understanding of statistics, it'll probably make more sense. And in fact, they rely upon these types of calculations. Now, we can crunch calculations using the binomial. What turns out to be true is that when we have a large number, so even at this case we're dealing with 53, as we build the binomial, let me get Brad's work off the screen. Probably don't need the z-score. As we build the binomial distribution, so we even started to do this with 2 rolls of dice or 5 free throws or something like that. As we build the binomial out and look at the distribution when n gets very large, when we have many attempts, it slowly starts to look like a normal distribution. Okay, as we build kind of the discrete case here, as n gets large, it looks more and more like a normal distribution. And that means that we can use our techniques. Eventually, it looks almost identical to the normal distribution. And so that means we can use the equations and the z-scores and all of that type of that process to do work with binomials as well. And that becomes quite powerful, again, computationally, trying to outline every different probability, of 50 or 41 wins and 40 wins and 27 wins and 53 wins. All of those, if we bring them up into a distribution, it's going to start to look like a normal distribution. And so we can use the concept of the z-score, the z-table, the percent likelihoods of being between different ranges. We can use the z-table to approximate the binomial, and that has pretty powerful abilities in our pretty powerful effects on our ability to crunch all of those different probabilities. So at the end of chapter 7, we turn and look at approximating it, and the big thing that you're going to have to kind of think about is how do we do that? But then there's this one little thing called the correction factor, and really the heart of that is that remember the binomial is it's a discrete situation, right? So these are, if we zoom in on one specific, the number of wins, 46 is a discrete value. And so the way that the distribution or the normal distribution deals with that, we want to build in a correction factor. And here's where, so if you wanted to say 47 or more wins, we would actually use 45.5 in our calculations. Okay, and that is to account for, this whole range counts as 46, and you can think of it graphically. It spans from 45.5 to 46.5. Okay, and that's really what the correction factor is after, is letting the normal distribution math accurately depict a discrete variable. And just like we talked about at the start of continuous variables, we need ranges of outcomes. And so that's what the correction factor is after. So if you have more questions about that, please let me know. But other than that, hopefully this helps you get down the path into your assignments. And so I'll stick on for a few minutes, or if you want to swing by office hours later today, feel free.